About 58% of all the electricity generated is used to drive electric motors. Keeping them operating correctly requires knowing what maintenance the different kinds of motors need and how to perform it, and how to test and troubleshoot motors when they do fail. In this program, we'll begin our study of motors by looking at their basic construction and operating characteristics. Let's start with the most basic fact about all electric motors. Any motor is actually an energy conversion device. It takes electrical energy and converts it to mechanical energy. Electric current is used to turn the motor shaft, and the shaft drives a mechanical load and gets work done. But there are also differences between motors. One of the most important is that motors come in various horsepower ratings. The higher the horsepower on a motor nameplate, the more powerful the motor is. To understand what a horsepower rating means, we have to understand a few other things first: torque and work. The load a motor is driving may rotate like a fan blade or pump impeller used to move air or a fluid, or the load may move in a straight line like a conveyor belt, or the mechanism which moves the cutting head on a milling machine. But however the load moves, a motor's shaft rotates. So the force it exerts is always a twisting or turning force called torque. A straight line force, or an ordinary push and pull, can be measured in pounds or newtons. But torque is measured differently. Take the case of a motor turning a winch. In order to lift this 50-pound weight, the winch must pull with a straight line force of 50 pounds. But how much torque will the motor have to produce? That depends on the radius of the winch drum. The torque a motor produces is measured by multiplying the amount of force it will exert times the distance between the center of the shaft and the point where the force is being applied. In this case, the rim of the winch. If the winch drum is 3 feet in diameter, its radius is 1.5 feet. So the motor must exert 75 pound-feet of torque to raise the load. What happens if the load is increased to 100 pounds? A motor will always respond to a change in the load by producing just the amount of torque demanded. So the motor will have to exert 150 pound-feet of torque. If the torque requirements are within its capabilities, it will move the load. Now let's look at the load a motor is driving. In applying force to move something through a distance, a motor is doing work. That is how mechanical work is defined: force in pounds, newtons, or some other unit, times the distance in feet, inches, or meters that the force moves something. If a motor exerts torque so that it is pulling with 50 pounds and that pull moves the load 10 feet, the motor has done 10 times 50, or 500 foot-pounds of work. If you wait until the load has moved 20 feet, the motor will have done 1,000 foot-pounds of work. Be careful not to confuse torque and work. Torque is a turning force, which produces a certain push or pull force at a certain distance from the center of the motor's shaft. Work is the force times the distance an applied force moves something. Now, when you look at a motor nameplate, you will not see anything about the work a motor can do or the torque it exerts. You will see a horsepower rating, however. Power is the rate of doing work, or how fast a particular amount of work is accomplished. Any motor, no matter how small, will do a lot of work if you wait long enough. A powerful motor will do the work quickly. To produce 1 horsepower, a motor must do 550 foot-pounds of work in 1 second, or 33,000 foot-pounds of work per minute. Power is related both to the shaft speed and to torque. The more torque a motor exerts, the larger the load that it will move. The faster the shaft turns, the faster a particular load will move. This simple formula relates torque in pound-feet and motor speed in revolutions per minute to horsepower. If a motor is turning at 1,750 RPM, for example, it must exert 3 pound-feet of torque to produce 1 horsepower. It will also produce 1 horsepower if it exerts 5 pound-feet of torque and runs at 1,050 RPM. Okay, now let's look inside a motor and see how it produces torque and horsepower. Mechanically, all electric motors have only 2 main parts or assemblies. One of them turns. It includes a shaft and rotor. A bearing supports the shaft on either end. The other part is stationary. It includes the stator, the frame, and the end covers or bells which support the bearings. Now, both the rotor and the stator are essentially magnets, and that's really the key to how a motor works. We don't know exactly why magnets behave the way they do, but all magnets have a north pole and a south pole, which are produced by a magnetic force or field called magnetic flux. The magnetic flux passes through the magnet and surrounds it. When you put 2 magnets together so that their north poles or their south poles are together, the magnetic flux of the magnets produces a force of repulsion. Like poles are pushed apart. But when you put 2 unlike poles, one north and one south, together, the opposite effect occurs. Unlike poles attract and are pulled toward each other. The stronger the magnets are, the more powerful this pushing and pulling will be. We fix these 2 magnets in place with unlike poles pointed toward each other, north and south, so you can see how a motor exerts torque. These will be our stator magnets. When we pivot a 3rd magnet, a rotor, between them, the forces of the magnetic poles will turn it. And as it turns, the rotor is exerting torque. But once the rotor's poles have lined up north to south with the stator poles, it stops. In order to keep generating torque, we must provide a way to keep the rotor turning. The only way to do that is to reverse the poles on either the rotor magnet or the stationary stator magnets just as the poles are lining up. The rotor magnet would then be pushed and pulled around another half turn. We can accomplish this if we replace our permanent stator magnets or rotor magnets or both with electromagnets. An electromagnet is a coil of wire wound on an unmagnetized iron core. Current in the wire produces magnetic poles just like those of permanent magnets. Which pole is north and which pole is south depends on the direction in which the current is moving. By reversing the current, we can reverse the poles. Now we can keep the rotor turning by reversing the current in either the rotor or the stator coils at just the right time. The magnetic poles reverse and the rotor swings around to line up the other way, exerting torque as it turns. If we keep this process of reversing the magnetic poles going, north to south, south to north, and so on, the rotor will keep turning in a circle and exert continuous torque. All motors use electromagnets for either the rotor, the stator, or both. These electromagnets can vary quite a bit in wire gauge and number of turns. In a DC motor, the current in the rotor coils is reversed by the switching action of brushes sliding on a commutator. The second of these lessons deals specifically with DC motors. In an AC motor, alternating current is applied to the stator coils, so the stator poles reverse automatically. We will look at AC motors, both single-phase and three-phase, in Lesson 3. Now let's look at how a motor is made and why. Most motors are heavy, and there's a lot of heavy metal, mostly steel and copper, in a motor. The copper in most motors is in the form of wire coils called windings. It conducts the current that creates the magnetic poles. In most motor windings, resistance is kept as low as possible because current flowing through the resistance causes heat. And as we'll see, heat is the main destroyer of motors. Since steel conducts magnetic flux much better than air, and allow stronger magnetic forces to be established, you'll find a lot of steel in a motor. Motors are built so that practically all the flux is carried by steel. Almost the whole frame and housing of the motor become part of the stator's magnetic field. The only place where the flux must cross through air is in the gap between the rotor and stator. This is a major barrier to it, which is why the gap is kept as narrow as possible. Another reason there is so much steel in a motor is that the air gap between the stator and the rotor must be accurately maintained so the rotor does not rub on the stator. The frame must be strong because the windings inside a motor are subject to high forces. Magnetic forces on both stator and rotor windings can actually force them out of position. So windings are lashed securely in place to prevent any movement which might chafe through the insulation. Rotor windings are subjected to centrifugal forces as well and are often banded to prevent them from flying out of their slots. Okay, we've seen how a motor is made so that current produces magnetic fields and how the magnetic fields produce torque and horsepower. Now let's take a closer look at the general operating characteristics of motors, how they behave under various load and speed conditions. We'll start with a motor running under no load. The shaft is turning freely at full or maximum speed, usually somewhat faster than the speed stamped on the motor nameplate. As you can see, even an unloaded motor draws some current. That's because the motor must overcome bearing friction and the wind resistance of the spinning rotor and fan. Now, most motors will slow down when a load is applied. The greater the load, the slower the speed, and the greater the current and torque. This basic relationship between load, speed, current, and torque is important to keep in mind, particularly when troubleshooting motors. We will see it applied frequently in later lessons. Here is a graph of what we have been looking at so far. It's called a speed-torque curve. Notice how load torque is 0 at the motor's maximum or no load speed. As the motor is loaded, speed drops and torque rises to meet the demands of the load. But there is a limit, of course. A particular size motor can exert only so much torque. If a load requires more than a motor's maximum torque capability, the motor will stall. As the motor approaches stall, current rises sharply because the motor is trying to provide the required torque. When operating under heavy loads at low speeds, motors will usually trip their overload breakers quickly. Even so, running a motor under high current conditions will soon burn it out. We can learn more about motor life as well as motor efficiency by taking a closer look at how speed and torque affect horsepower. If we plot motor horsepower output along with torque, we see that both are 0 at no load. 0 torque means 0 horsepower. At stall, horsepower is also 0. Nothing is moving and no work is being done, even though the motor is drawing a lot of current. Anywhere in between stall and no load, a motor does produce horsepower. At rated speed, it produces its rated horsepower. Now, as we said at the beginning, a motor is a converter of electrical energy into mechanical energy. Its efficiency is a measure of how well it does this. Efficiency equals the mechanical output in horsepower divided by the electrical input in watts. Watts of DC power equals current times voltage. When the power is AC, the relationship is a little more complicated, but the watts consumed by a motor always depend directly on the voltage applied to it and the current it draws from the line. Most motors operate at a fixed line voltage. This means that the watts into a motor depends largely on the current into the motor. So if we plot watts of power being consumed by a motor against its speed, the curve looks like the current curve, or the torque curve for that matter, since the torque a motor exerts to drive its load depends on the current. We can see how the efficiency of a motor varies if we plot watts and horsepower together. As we've already seen, at stall, the motor is producing no horsepower, but the watts input to it is very high because the motor is drawing a lot of current. At no load speed, watts input is low, but horsepower is zero again, so efficiency is zero. At rated power, a motor is consuming a lot of watts, but also producing a lot of horsepower. The efficiency is quite good. Now, what becomes of the watts into a motor that are not converted into horsepower? They get converted into heat. 1 horsepower equals 746 watts. So a perfectly efficient motor would produce 1 horsepower for every 746 watts of power consumed. In practice, since motors are not perfectly efficient, it always takes more than 746 watts to produce 1 horsepower. The extra watts heat up the motor. Of course, anyone who works around motors knows that they get hot. They will heat up fastest at stall speed when they are consuming a lot of watts, and all those watts are converted to heat. Operating under heavy loads at low speed is almost as bad. At maximum power, the efficiency is high, but the difference between watts in and horsepower out is still large, and a motor will heat up if it is operated under these conditions for very long. At rated horsepower, a motor will heat up comparatively little. In fact, this is what rated horsepower means. It is the maximum horsepower a motor can produce without heating up so much that the insulation inside is likely to be damaged. What all this means to the person responsible for the proper operation of motors is that motors must not be overloaded or expected to produce more than their rated power for too long. In practice, much of motor maintenance involves keeping friction low in motors and associated equipment. High friction increases the load on a motor and makes it more likely to overheat and burn out. Maintenance also should ensure that a motor can get rid of any heat that it does produce. Installing and connecting a motor requires careful attention to the setting of the overload breakers. They monitor the current to the motor and trip open when current is more than rated full load current for too long. Their purpose is to prevent a motor from burning out under overload conditions. Troubleshooting a motor often means detecting when a motor is overloaded and locating the cause. Maintaining and troubleshooting motors both require a good understanding of why motors fail and how to keep them running at maximum efficiency. In later lessons, we will look more closely at various types of motors and how to work with them.